I am feeling very nostalgic because just last week I was here with you and now this room is very familiar. So, there are certain announcements to share my thoughts as well. It was truly nice to meet you all in Addis Ababa University. We all had a nice time with you all. I would like to thank you all for giving me such a good feedback. And as per the feedback, many of you wanted to know what are the course plans. So, I am showing you the course contents here, which I have already uploaded, and the file name will be content.pdf, okay, content.pdf. To share the course contents with you, we started May 15th and hoping it will go up to September end. I just put a question mark there. We will have 28 lectures. The textbook already you know, Introduction to Robotics by S.K. Saha, 2008. The first reprint came in May 2009, which takes care of many of the typing mistakes. And the bottom is the book's website, which gives many details about mostly the figures of the books, which I am also providing to you as .pdf. So, if you recollect, between May 15 to July 21st, we have covered the following topics. In lecture 1, we had introduction, which is a part of chapter 1 of my book. Lecture 2 was robot subsystems and classifications, which was chapter 2 of my book. Lectures 3 and 4 were on actuators, chapter 3 of the book. Lectures 5 and 6 were on sensors, chapter 4 of the book. Lectures 7 to 9, that means 3 classes, were on transformations, chapter 5. Lecture 10 was on mathematical fundamentals, which was an appendix A of the book, and lecture 11 to 14 we had a topic on kinematics, which was chapter 6, and we had a lot of interactions, clarifications. We had a mid semester exam on July 22nd in your university. So, topics which are to be covered today, we will start with statics, hoping we will be able to finish in 2 lectures. Then it will follow by dynamics. We will have a couple of lectures, maybe I have put 17, 18, 19, 20, 4, maybe 5. Then we will have lectures on control as well, 21, 22, 23, about 3 lectures. We will have about 3 lectures on motion planning as well, which is nothing but the trajectory planning, chapter 11 of the book. We will have about a class to discuss about different types of programming, which is chapter 12. As some students asked during the interactions, I really do not intend to teach you a particular programming language. I just wanted to give you some outline of how the programming in robot control is done using some of the existing programming languages. So, I am not going to really teach you programming so that you can program a particular robot, because there are different robots and there are different programming languages. Even the one you have on Mitsubishi may have a different language, which I may not be aware of. So, coming back to the last topic for this course will be on industrial applications. There is no chapter on the book. I intend to share separate materials with that. For example, welding applications, pelletizing applications, so and so forth. There was also request in the feedback about the design aspects. In these topics, I have not put anywhere, but I will try to see if I can save some time somewhere. So, at least if one class I can devote on the design. So, as per feedback, I will try to introduce the robot design aspects also. So, this I have already uploaded in the website, so that you know what are expected. Okay, so coming back to today's lecture, the outlines of today's lecture 15 on statics I have uploaded as 15 lec.pdf, and also all the figures of this chapter, chapter 7 fig.pdf. So, let us take a review of lecture 14 which was delivered last week on physical interactions. So, we talked about link velocities of the robotic systems. We derived a Jacobian matrix, and how Jacobian is important to define a singularity. For example, if a two link manipulator is singular, one of the singular would be the positions where the robot cannot move, like my extended hand. Okay, you look at my hand here. So, if I give a point here which is outside the reach of my hand, so it will show you the singular, which means the determinant of the Jacobian matrix will be 0. That means it cannot reach. And then we discussed there about two link manipulators. So, in this chapter, chapter 6, we had one section on acceleration analysis, which I am skipping because whatever accelerations we need, that will be for dynamics. I will do it when we go to dynamics chapter. So, for today's topics, we have the following outlines. So, we will define statics in the context of robotics. Then we will determine the link forces and the moments, and we will see the recursive formulas. That means knowing the force in the end effector, calculate the forces on the other links, and we will do the examples. Not only do the examples, I will do it by hand, so that you can understand each and every step, and then the summary. So, talking about the definitions of statics, the first definition is the definition which we learned in our high school. Statics is the branch of applied physics concerned with the analysis of moments and forces acting on a system that is in static equilibrium. So, if the object is not moving, that means applied forces are keeping it in stationary conditions. We would like to know where and how much forces are acting on the system. Coming to robot manipulators, the relationships between the joint torques and forces and the Cartesian moments and forces at the end effector are sought. Now, looking at my hand again, suppose I want to I want to hold an object. Okay. On my hand I have an object is heavy, I want to keep it in these positions. So, object has certain mass and the weight which is acting downwards, and my hand has actuators here and there. So, they are both holding it. So, now it is in a stationary position, that means it is not moving, right, it is in stationary position. So, what are the torques to be applied at my shoulder, at my elbow, to be able to hold the object. So, that is we call it a static equilibrium, and the torques which we calculate are those to maintain this object in stationary conditions. So, that is the problem in statics of robotics. Now, we would like to now do the calculations for which we define certain vectors. Okay. Let us look at this diagram first. So, I have taken out one link from the robot arms, and in this link we define the following quantities. First, remember this OI. This OI is the origin. So, this OI is the origin of the ith frame. Notice that xi, yi, zi, that xi, zi and wherever is the corresponding ya would be, we have defined that it is fixed to I minus first link. However, at this junction, that means OI, both links, that means link I, this is my link I, this is my link I, this is my link I. The link I and I minus 1 are contacting with each body. So, I can consider that if I minus first body, which I am writing it here, that force F I minus 1 comma I, that means the force applied by I minus first body, which is sitting next to it, to I. So, the force is applied by I minus 1 body to ith body through this point OI. Okay. Similarly, this OI plus 1 is the origin of my I plus first frame, but at this junction we can imagine that the I plus first body is applied force at this point. In actual scenario, this could be your I plus first body, maybe for physical contact is happening here. Okay. So, force actually may be applied at this surface here, but for the mathematical calculations we transfer these forces here, and we consider that I plus 1 body are applying forces and moments through OI plus 1. Physically it may happen here, but we must consider it here. Similarly, I minus 1 may be physically in contact here, but whatever force is being applied here, we transfer it here and consider that all the forces from the I minus 1 body is applied through this. So, this is for the mathematical formulation purposes. Whatever the physical forces applied here, we consider with respect to this point. Whatever forces are applied here, we consider with respect to this purpose, because the origin of the ith frame is situated here and origin of the I plus first frame is situated here. Okay. In many practical cases, they may be sitting where I have shown. So, OI plus 1 may be sitting here itself, OI minus 1 may be sitting here, as you have seen in many of our examples. Okay. So, let me clean it. So, clean it. Okay. Oops. Discard. Okay. Okay. So, what I told in brief, all the forces applied by I minus first body, we assume it is applied through OI. Whatever the forces applied from the I plus first body is applied through OI plus 1. Then from OI to OI plus 1, OI to OI plus 1, this is our I vector. Then if the mass center is located here, from the origin of ith to this is our di, then from here to the next one is ri, which means di plus ri is equal to ai. Okay. And Now, I will be defining formally in the next slide. So, f I minus 1 comma I, a 3-dimensional Cartesian vector. This means it has a x component, y component and z component. So, 3D vector of resulting force on I by I minus 1 at OI. The meaning of resulting force is the one which I was telling you, that physically it may be somewhere else, but we are taking with respect to OI. Then n I minus 1 comma I is the 3-dimensional vector, that means it has a component x, y, z of resulting moment on I by I minus 1 at OI. Similarly, for the I plus first body to I 3D vector of resulting force on I by I plus 1 at OI plus 1, n I plus 1 comma I is the 3D vector of resulting moment on I by I plus 1 at OI plus 1. Notice that the force applied by I plus first body to I is equal to minus of force applied by ith body to I plus 1. This is Newton's second law. The action and reactions are same. If one body, that means I plus first body is applying this much force, if I plus first body is applying this much force given by I plus 1 comma I, then the force applied by the ith body to I plus first body should be negative of that one. So, I have just written that, there is nothing very fancy there. Similarly, with the moment applied by the I plus first body, which is here I plus 1 comma I, is equal to the moment applied by I to I plus 1. Okay. So, it will be minus, because this we will use whenever we need to simplify the equations. G is the G is the 3-dimensional vector. G is the 3-dimensional vector which is the acceleration due to gravity. Di, I have told you what is di. Di is the 3-dimensional vector denoting the position of the mass center of the ith link Ci relative to the origin of the ith frame OI. So, di is the vector from OI to Ci. Ri, accordingly we define a vector from Ci to OI plus 1, and Ai is the 3-dimensional vector of OI plus 1 with respect to OI, such that this is Ai is equal to di plus Ri. Let me now show the figure again to show all those vector quantities. Okay. So, here you have f I minus 1 comma I, that means force applied by I minus 1 body to ith body. This is the force, not force, moment applied by I minus first body to ith body. This is the force applied by I plus first body to ith body. The way I have written it here is minus of f I comma I plus 1, that is the Newton's third law, action reactions. So, similarly the moment here, the gravity is causing a force MIG, which is this force directions MIG. This vector is AI from origin I to I plus 1 origin. Then this vector is divided into two vectors. So, one is di is to OI to CI, OI to CI, and then CI to the next one. With all this vector quantities defined, now I can write very easily the equilibrium equations, which we will do now. But if there is any doubts here, I can wait about 15 seconds to see if there are any questions about the vector quantities. Are the cordless mics are in place? Hello, Dr. Tafese. Nice. Are the cordless phones in place? Sorry, not phones, cordless mics. Okay. So maybe the students should start using it. Okay, no questions. So we proceed. Maybe we can test questions can be asked to see whether cordless mic is working fine. Somebody from the last bench? Hello? Yes, I can hear you. You have any question? Okay, so I think maybe whenever somebody from the last bench or maybe in between, which I cannot see it very clearly, they may raise and ask the question. Can you raise? Can I see who is holding the mic? Oh no, stand up. Stand up. Okay, good, good. Now I can see. Okay, thank you. No questions. Please sit down. Okay, so now what we do is the free body diagram. That means one link I have already shown you. Now let us write the static equilibrium equations. The first one is the force equations, right? So we go back and see what are the forces acting on it. So if you look at this diagram, now what are the forces? One force is here, one force is here, that means the force which I minus first body is applying on the ith body. There is another force here which is due to the force applied by I plus first to ith body. Instead of I plus 1 comma I have just put minus I comma I plus 1 because that is due to the Newton's third law. What is the other force acting on it is the gravity force, right, MIG. So these are the three forces acting on it. If I say I minus 1 comma I is towards the ith body, so this is one force, then this is another force. So I can write F I minus 1 comma I, this force plus this, which is actually minus F I comma I plus 1, then plus MIG should be equal to 0 when that is in static equilibrium. That means no motion being applied on it. So this is the same thing I have written here, F I minus 1. So I have written it here, F I minus 1 comma I minus F I comma I plus 1 plus MIG is equal to 0. So this is the force balance equation. Now I write the moment balance equation. No? So moment applied by I minus first body to ith body is this much, then due to the interaction with I plus first, which is this much, then there are component due to there are component due to I plus first force applied to ith force, okay. That is this much, and then di comma mi di cross mig is this much. You must be wondering what happened to the force applied by I minus first body to ith body. Let me go back to the paper to show how I am writing it. Okay. So, here I have f I minus 1 comma I, then I have n I minus 1 comma I, then I have minus f I comma I plus 1, and then you have n minus I plus 1, then this is O I, this is O I plus 1. So, this vector is d I where mig is acting, then this is a I, then this is r I. Okay. So, actually I am writing the moment balance with respect to O I. So, I am writing moment balance with respect to O I. So, I am writing first n I minus 1 comma I, then whatever moment is applied here throughout this body anywhere will be the same moment. So, that is the reason I wrote this one. So, this is taken care of, this is taken care of. Now, the force f I minus 1 comma I is acting at this point. So, it will not have caused any moment. So, nothing due to this component. However, this and this will cause a moment. So, first I will consider this one. So, this is at A I cross f I comma I plus 1, and then here I have plus d I cross m I g equal to 0. You may be worried little bit, how am I writing minus a I cross f I and here plus. For that, let me show you a simple illustrations. Suppose I have a rigid body, okay, and I have applied a force here f I. Okay. Now, we know that if I now want to calculate what is the moment about O I, or let us say just a point O. So, moment about O I O is this vector, let us say this is a vector, okay, A cross f I. So, this is equal to A cross f I. Okay. So, first we go to the point of application, which is my vector A, and at that point of applications a positive force f I. So, moment about O is equal to A cross f I. This can be very simply checked. Suppose if I have a rod, and then you have put a hinge here, or you have, and then I apply a force F. Okay. Now, this we know, and if this length is A, so we know moment about this point O, about O is equal to A into F, and the direction will be in anti-clockwise direction. Okay. This is known from our high school knowledge or first year knowledge. If I apply this, forget about this I, let me apply this formula and see whether this is correct or not. For that I assume this is my x axis, this is my y axis, and this y will be my z axis. So, the f vector, this f vector has component. So, f vector has a component along y directions. So, it is 0 scalar component f and then 0. Okay. Then this a vector has a scalar component distance a along x. So, a 0 0. Okay. Now, if you apply a cross f, that means this formula. So, a cross f. So, let us put it cross f. So, I put this 0 f 0. If you apply now the cross product rule, so this expressions will become, I take it to the top, So, a cross f is will be equal to, so this will be 0 0, then 0 0, and the last one will be a f. So, a cross f tells that you have a 0 component about x, 0 about y, and a f about z. So, a f, and we know this is the one from our high school knowledge, and this is the positive z. So, whatever formula, the cross product formula we have learned here, we have tested for a simple exercise of a cantilever beam, and we saw that a cross f gives me that a 0 0 a f. Now, suppose same rigid body, I ask you, a force is applied like this, and I want to calculate the moment about this. Okay. And somebody told you that that this vector I know this vector. Okay. So, now the way I have taught you that for me moment about O is equal to distance vector to the point of application of force cross force to that point. Okay. Which means what? Distance vector to the point of application. So, this is my distance vector. So, this vector is actually minus of a. If this is a, somebody told me, as per my definition this is minus a. Then force to that point, which means force to that point is this one. So, if this is F, this will be minus F. So, if I now apply as per our knowledge A minus F, which will be A cross F again. So, now another case, if I show you that now this is the force F and this is the vector A. So, the moment will be minus A cross F. So, please do not get confused when we do this kind of a minus plus minus plus. Okay. So, now if I show you here, which I have done it should be camera actually coming. Can you see my hand?